So, hi guys, my name is Vijay Gajanan. I'm a micro student ambassador from UAE. I graduated from Pispilani Dubai campus and I majored in computer science. And right now I'm currently in transition to my master's degree. So yeah, so I currently research deep learning applications in for medical images. So that's my area of interest. And yeah, let's start let's start the session. So in today's session we'll cover searching algorithms, we'll cover sorting algorithms, and we'll also be and also I'll be giving you an introduction to certain paradigms of problem solving. So these paradigms can be are like are like called because of the way that you solve the problem. So in today's session we will talk about divide and conquer, but tomorrow we'll start out. We'll also talk about greedy algorithms as well. And in tomorrow's session, I'll also be taking tomorrow's session as well. And I'll also be teaching you about hashing, hash tables, and linked lists. And Harsh, our other presenter, will be talking about matrices. So yeah, let's start, guys. So, as the name implies, a search algorithm is an algorithm that finds and retrieves information that is stored in a data structure. And this information does not need to be only the element itself. It can also be the index of the element. So, if you ask the array, hey, what index is this element at? It'll give you back the index, so the I value, or you can also ask to confirm whether the element actually exists. And in that case, you can just return back the search value. Or let's just say if you're working with dictionaries or or I would say a vector or any kind of key value pair kind of system, you would be able to of course there are ways to access the element directly in those data structures. But if you do it in an iterative manner, you can do that as well. And you can also search for substring in a string. Many languages like Python support substring search as well, like just inbuilt functions. So yeah, searching is an important type of algorithm because you'll be using it almost everywhere. So you have A star search, you have BST, you have DFS, no, not BST, sorry, BFS and DFS. So searching might seem simple, but there are so many ways to do it, and and in some problems, no, you can only find an almost optimal solution, I would say. So yeah, let's move on. So let's start with the most simplest kind of searching. It's linear search. It's equivalent to like taking a pack of cards, and I tell you, can you please give me the king of hearts? What will you do? You'll open up the pack, and you'll search. Like you'll remove the first card from the deck. If it's not there, you'll keep it down, and it's an iterative process. It keeps repeating until you hit a match, or else you return with a or you return with a false condition. Okay, so linear search is the simplest of all search algorithms. So as the name implies, you linearly iterate through the entire data structure step by step. Yeah, and in linear search, you do it step by step. So like by a count of -1 or +1. And if the search item matches the element that you want to find, you either return the element or you return a false condition. And this false condition can be anything. It can be just uh, returning the Boolean value false, or in some cases you actually give back -1. So the best case for performance for linear search is when your search element is the first element itself. So to give you an example, can I exit out of this? Sorry about that. So to give you an example, if I have this array, so if I call this function linear search of 6, it's going to give me true, or it's going to give me the 6 value, or it's going to give me the index value, which is actually 0 in this case. One thing to note is that not every language has the index starting from 1. So if you see pseudocode on, let's just say, Wikipedia and all, right, sometimes they'll say for all elements of elements starting from 1, 2, 3, 4. In many programming languages, it's going to be 0. But in some languages like R, MATLAB, I think Lua, Julia, and in all these languages, right, your index for your array or any kind of data structure actually starts from 1. So do keep that in mind, okay? So it's not necessarily it's 1, it's just signifying the first element. So in this case, my search value is always going to give me the same result because it is 6. So if I keep calling the first element, it's going to give me the same constant time, like it's going to be the first element directly. So that's why the best case performance, I'm just calling it BCP, it's O of 1. But let's just say I keep calling the last element. In this case, it's going to be 4. So even though this list has 8 elements, it's actually the 7th index over here because we're following from 0, 1, 2, 3, 4, 5, 6, 7. And in this case, our worst performing one. Let's see. So worst performance. Okay, sorry about this. So I won't use this terminology anymore. It's so confusing. So O of n. Well, why is it O of n? Simply because I have to iterate through the entire array. I have to keep checking. I have to perform at least n comparisons. I have to keep checking. Okay, is this element equal to if I say linear search of 4 in this case, does this equal to 6? No. Equal to 5? No. 3? No. 1? No. 8? No. 7? No. 2? No. 4? Yes. So I have to go through. I have to compare at least like n minus 1 times. So in that case, I am performing the worst in this case. So now it is O of n. So of course, it's a simplest. So your best case performance. Okay, so best case performance is O of 1. On an average case, actually, if you do some analysis on it, it will perform actually n minus 1 by 2 comparisons. If I'm not wrong, so I think this is like I'm pretty sure it's n plus 1 by 2 comparisons. In that case, O of n plus 1 by 2 is honestly equivalent to n by 2. So in algorithm analysis, you pick the biggest biggest parameter. So it's this one. So, and of course, divide by 2 is just a constant, so you just remove it. So it's still O of n. And worst case scenario, if I have to do all the comparisons, it's going to be O of n. So the pseudocode for this is quite simple. I'll just present it so it's in full screen mode so all of you can actually see it. So this isn't pseudocode, by the way. This is not in any specific language. So you can use any kind of loop. You can use a while loop if you want. It's any kind of looping system. Not a big deal. So you iterate through. So since I'm think of it as an for current high-level languages, I think it starts from 0. So 0 till the last element, and you keep incrementing by 1. Of course, it's step by step. And if my array finally hits the search value, in this case, I'm returning the search index of I, else return minus 1. One thing to notice that minus 1 is an actual index in Python. So don't get confused about this being an actual index. It's just giving you back a false condition. Okay, so think of this as a true condition. This is the false condition. Okay, so we're done with a linear search. Now, linear search is kind of slow if your array is a bit huge. So we can actually optimize this by instead opting for binary search. But here's the thing. Binary search requires that your array is sorted already, whether it's in the ascending or descending order. So how does binary search work? So at every iteration, it will try to find the middle value. If the middle element does not match the search value, the search range is readjusted based on the middle value. So to illustrate this point, I'm going to go back to the whiteboard and I'm going to show you that. So let's try getting rid of all this stuff. Okay, wow, this is I need like a bigger eraser. Oops. Now this is nice and big. I can just wipe away. Okay. Okay, I think we're almost done. Okay, so let's go back. to our drawing. So our middle element in this case would actually be 3. I would say, because let's just go to this. It's easy to explain with the algorithm, I would say. So let's start doing this algorithm like step by step, so that you also can get an idea on how to solve this problem. So what's our left index? It's going to be the zeroth element. It's our first one. So it's this. So if left index is equal to 0, and of course, since we're following the zero-based rule, like zero starting, like index, 7 is our rightmost element. This is the index, by the way, not the actual element, value itself. So our middle, even though it's going to be 3.5, 3.5 isn't actually a valid one, a valid index. So we usually take the floor value. So in this case, it is actually going to be 3. So usually in even numbered cases, even number of elements in the array, so that's why we take the floor function. This thing, because of the indexing. Sorry for making it confusing. So what's our middle element now? The third index position, 1. So let's set a search value now. Okay, let's just say my search value, I want to find, okay, let's find 7. Let's find 7. So we know that the middle element now is actually, okay, I am very sorry, guys. This array needs to be sorted. My apologies. Honestly, I'm very, very sorry about that. So I'm very sorry about that. But never mind. I can try making the array like that. So not a big deal. So I'll just make it as 0, 1, 2, 3, 4, 5, 6, 5, 6, 7. Okay. So now we're back on track. Okay, we are allocating the indexes 1, 0, 1, 2, 3, 4, 5, 6, and 7. Okay, now we're still on track, not a big deal. So our middlemost element now is 3, but we know that the middlemost element is actually very less than our search value. I'll just indicate the search value by this small box over here. I want to find this value. So now we see that it's actually bigger. So now we readjust the middle and we readjust the left and right. So we're technically making our range to search a much small. So now our left value will be updated because we want to search in this area. How do we do that? We readjust the left value. Left will now be middle plus 1. So now I'll be searching in this area, in this subarray. Okay. So now we'll again repeat the process. Now our new left is 4. Our right has not changed. And now our middle element is 4 plus 7, which is 11 divided by 2. It's actually 5.5, so it's going to be 5. So our fifth element is now 5. Our new middle is 5. Again, it's not, it's still smaller than our 7. So we're going to do it again, one more time. So now again, our middle will get updated. Middle is now equal to 5 plus 1, 6. So I'm going to search in this area. And now 6 plus 7 by 2 will give me, again, 13 by 2, which is 6.5, which is going to, it's the floor value, it's going to give us 6.6 actually. So again, it is not 6 is again less than 7. We'll do this one more time. And now our middle is equal to 7. And by the way, before we calculate this middle value, we check if the middle is actually equal to the search value. So now my search value is finally equal to, my search value is finally equal to 7. So if I do array of 7, does it equal to 7? Yes, it does. So now we return this value. So this is what's being seen over here. So please load. Is this not loading? It's all right. Can people see the text over here? Can somebody confirm? Okay, this is good. It's back to normal. So yes. So as long as your left index, so you're trying to stay in the you're trying to stay in the you're trying to stay in the range. So as long as you calculate the floor value again, and then this should be actually that's not equal to, by the way. Sorry about this mistake over here. So you keep checking if the middle index is actually equal to search value. If it is so, you return the middle index. Else, if your array middle is actually very large, you actually subtract. So this is the other case which I didn't discuss about. In the example that I gave you, we actually searched by incrementing the middle value and giving and assigning it to the left index. But just suppose you are trying to find, let's just say, one over here. In that case, you would try to search in this subarray, starting from the first middle element. So in that case, your left would not change. Your left is again 0 over here, but your right value, this one, would be middle minus 1. And you'd repeat the same process all over again. So one thing to note about binary search is that its average case performance is log n and worst case performance is log n. But how are we getting log n? I'll explain this to you guys. Yeah, just clear, please. Clear my entire screen. Thank you. So now see. So now so let's just say n is our number of elements, and x is the number of times you need to divide n to get 1. So if I have an array that has n number of elements, how many times should I divide it by 2 to get only one element? That can be represented by this relationship. So what is dividing by 2, guys? So if you divide, let's say 4 divided by 2, you are actually dividing it by 2 raised to 1. And suppose, 4 divided by 2 is 2. 2 divided by 2 raised to 1 is again equal to 1. So I'm dividing it by 2 raised to 1 twice. So technically, these two operations are actually true, which is actually true. So that's what I'm asking. So if I want to divide 4, I need to divide it by 2 times to get 1. Similarly, I'm asking that how many times do I divide by 2 to get 1 if I have n number of elements? So if we take this relationship, okay, guys, and now we actually solve it. And if I apply log on both sides, by the way, so we know that log is actually anti-exponent. So I'll just do steps one by one so that you can understand. So now x log 2, and we're interested in x, by the way. So x is equal to log n by log 2, and we know this to be actually log to the base 2 of n if you know your exponential properties. But again, this 2 is just a constant, so you can just make it as log of n. So that's why our best and worst case, our general worst case performance for our binary search is actually log of n. Now, when do we get log of 1? O of 1. I'm so sorry about that, guys. So our worst case performance is O log of n, and our best case performance is O log of 1. But how do we get this O log of 1? What's the first operation that you do in a binary search binary search algorithm? You calculate the middle. So if your search element is the middle element, it's going to constantly give you back that it's going to give you that element back in constant time, since that's the first thing you're calculating. So there's no need to divide the array. So that's why you get the best case performance when your search element is the middlemost one. In terms of binary search, in terms of linear search, the best case performance is when, it's the first element that you're trying to find. So there are a number of other binary searching algorithms, but they all involve graphs. So Harsh will soon teach you about graphs, so don't worry about that. And there's so many algorithms that you can do on graphs, and just learning these basics of searching will help you definitely. So now let's move on to sorting algorithms. Oh, sorry about that, guys. I'm so sorry. So as the name suggests, it's an algorithm that tries to sort items in a sequence in a certain order. Now, this order does not have to be numerical in nature, okay? It can be also lexicographical. So, lexicographical means, you can arrange, you might have to, sort all the characters in the array based on the ASCII value, maybe, or maybe based on its actual alphanumeric order. So, it's a possibility. It can be any order, but the essential fact is that you're trying to sort it in a meaningful way, basically. Now, this is like the I think it's like the first sorting algorithm that everybody learns. It's called bubble sort, and there are a number of ways to do bubble sort, and and even optimize it like even a bit more. But usually, the bubble sort that we usually start off with, in 11th or 12th grade, is actually the standard bubble sort, in which you keep comparing and adjusting the elements. So if I gave you a row of cups, let's just, those party foam cups that you get, for your celebrations and all. So and then if you write like random numbers of them, and you keep them in a line, and I ask you to sort them by only allowing you to move two adjacent cups at a time. That's what bubble sort is. So if you don't have any other rule in that, you are usually performing bubble sort. So bubble sort is one of the simplest ways of sorting. If an array has n elements, go to the list n minus one times, compare the adjacent element, and keep swapping if they're in the wrong order. And the best case for performance is O of n. This is when there is no need to sort any of the you don't keep sorting, and if it's in the same order. But the worst case performance is when usually the sequence is reversed. So that's O of n square. So this is the bubble sort algorithm. It's kind of easy to understand. So this is a variation of bubble sort in which you start off with the n minus one element. So as you can see that every time we have now this is in the case of this is in the case of if this bubble sort is in the case of when you have when you require an ascending order array. Okay, there is one also for descending order. All you have to do is change a bit of it. But in this case, of course, when the previous element is actually larger than the current element, you have to. So this is actually not the Python way of actually comparing swapping elements, but this is like the standard way of swapping elements, what you would do in Java or C++. So you create a temporary variable and you swap them. So let's try a much more optimized sorting algorithm. So this sorting algorithm is called merge sort, and it utilizes a algorithm style called divide and conquer. And you'll see why by showing you the by showing you the algorithm. So actually I should actually I'll actually talk to you about divide and sorting algorithms first. It'll make much more sense then. Let's do that. So divide and conquer. So these, Prashita talked to you about recursion today, and now we'll be seeing an application of that right now. So in divide and conquer, the algorithms use multi-branch recursion for solving problems called and they're called divide and conquer algorithms, of course. So you divide the problem into. So we all know that actually, like solving an entire problem by yourself is actually hard. So you create, so you break it down into steps. Same thing, you divide the problem into at least two subproblems of the same type. You do recursion. You solve those subproblems, and then you finally combine the output of those subproblems into the final output. And let's see how. So this is a very nice depiction of what you mean by divide and conquer. So you have one main problem. You do recursion to divide the sequence or array into like several subproblems. You then solve that small array. You just solve the issue in that small subarray or subsequence or any kind of data structures that you're working with, and then you finally combine those two into the final output. And now we'll see how it works with merge sort. So this is these two slides are the complete thing of merge sort. Don't get too scared of this, guys. Okay, just letting you guys know. Okay, so it's actually easy. I'll show you guys right now. So let's go to book. So let's go back to a whiteboard. Let's clear the entire thing. Okay. So let's take an array. I should write a bit small for this question. Okay. I'm so sorry. Sorry. Okay, let's start. So now we have 3, 1, 2, 4, 5, -2. How many elements do we have? I'll keep. Yeah, I think six elements are good. Yeah, I think they're good. Actually, I'll make it 8. Sure. So let's just keep 1 9 over here and 1 7 over here. Okay. So now we have 8 elements. So now when we perform merge sort, we first break it into numerous subproblems. So now we have 8 elements over here. Let's perform our first loop. In our first loop, we'll find the middlemost element. In this case, it's actually 4, I would say. So until you hit 4, you'll divide it into two sub arrays now. 9, 3, 1, 2. Our first subarray is done. Oopsie, that's not the right number to see. Okay, 4, 5, -2, and 7. Okay, and now we'll have, let's just see right here. Yeah, so again, we can divide it into two. So since we have even number of elements, it's actually easier to divide. But if you had like 3 or something, you would take the floor value. And in that case, suppose this had like 5 elements, you'd have 2 and 3. That's not an issue. It's just like, not a big deal. Now we'll again divide 9, 3. 1, 2. And again, we have to divide this side as well. So this keeps going on until you have only one element in each subarray. So we'll just keep going, guys. 4, 5 in this subarray. 2, 7 in this subarray. And we'll keep going again. One more time. We have to do this. So now, okay, let's zoom out of this. I'll just check it later. So now we have 9 in its own subarray. Don't think it's just the number, guys. It's within its own array, by the way. You can still have single element arrays. 1, 2. Okay, my 4 looks weird. 5, 4, 2, and 7. Now we've hit the final part. So now we need to combine these problems. So how do you do that? I'll just create some extra space for myself. Yes, now we can work on it. Okay, so now since I have two subarrays, now here's how it goes. You compare the first element of each subarray and check which one is larger. Depending on the which one is larger, you add to a result array. So this is your left array, your right array, and you'll have one result array on each combination step. So now, okay, I need to make it RE. Okay. So which one is larger, guys? 3, right? So now when we combine, 3, 9 is our input. 2, 1 is our output. 5, 4 is our output. Oops, I am very sorry about that. 2, 7 is our output. Now again, let's combine. Now this is going to be our new LA, RA, and this is going to be our resultant array. Okay. So now since you have more than one element in each subarray, now we have to be a bit careful. Okay. Now what's the first element of left subarray? 3. What's the first remaining element? First element of right subarray? 1. Which is larger? 1 goes first. So now So now we pop that element off. Okay. So now we only have 2 remaining in the other one. So now let's compare. What's the first element of right subarray? 3. What's the first element of right subarray? 2. Which one is larger? Which one is smaller? This is in ascending order, guys, by the way. 2. This is gone. So now since and when we do this operation, we have a condition that both these subarrays are actually not empty. Now, since the condition of this subarray has invalidated that, we go on to the next step. If there are any other subarrays in which you have to rearrange, all you have to do is just add the remaining elements. So now we have 1, 2, 3, 9 in now this thing. So if I follow the same steps over here, I'll get 2, 4, 5, and 7. Okay. Now, I think this will be our last iterative step over here. I'll just span a bit down so you can see what I can see. And now let's do one more time. This is our left array, right array, result array. Now, what is our first element? 1 versus 2. Wait, do I have two 1s? Or did I do a mistake somewhere? I'm so sorry, guys. Ah, my goodness. I did a mistake. I am very sorry about that. It's -2. But luckily, I don't think it did much of an issue because it was -2. So I'm so sorry. Okay. So which is the smallest now? -2. Pop it goes. 1. So 1 minus 4. 1. Pop it goes. 2 minus 4. 2. 3 minus 4. 3. 9 minus 4. 9 minus 4. 9 or 4. 4. 9 or 5. 5. 9 or 7. 7. Now this breaks the loop of adding the elements because this is empty, is actually false, is empty, it's actually true. So now we escape out of it, out of the loop. Now we have remainder elements in the left subarray. I will just add that, and now we have our sorted array. And this is how merge sort works. So now we can see that by just using a bit of recursion and a bit of intuition, we can see how that we can just make a much more efficient algorithm of merge sort. And just like the previous example, since we're dividing it into multiple what do you call this? I'm sorry about this. Into multiple recursion steps. That's why the best case performance is usually n. And in the case of worst case performance, which you have to go through all n sublists, you have to have it be O of n, big of n. So this is a very good algorithm. You can even look at quicksort, which is also similarly good algorithm. Right. I think I've covered all the slides for today. Tomorrow I will do a couple of lead code questions with you guys, like simple questions based on divide and conquer. I'll also give you an introduction to greedy algorithms. So you have questions like knapsack, in which you take the greedy approach, in which you don't care about the possible optimal output, but optimal maximum, like the global maxima or the global minima. You only care about the local maxima, the local optima, local minima. And we'll also be talking about what hashing is and how we use it in, let's say, hash maps or hash tables. And we'll also talk a bit about linked lists. Linked lists are quite important, especially if you maybe work with trees, maybe. And also tomorrow, Harsh will give you a good introduction to matrices and how they're used in and a couple of interview questions as well. So I know that this session was kind of short, but I wanted to explain these algorithms in a bit more detail. We'll have more much more coding maybe tomorrow. But before that, I just do want to show you the algorithm for merge sort. So this is our breaking condition over here. That's if the length of the array is 1, in which we've seen single element array, we start combining immediately. So that's our return condition. So you have the left and right subarray, and you just divide it into 2, and so you allocate you randomly allocate the elements, no, not randomly, you take whatever elements until the middle of the array, make push it into the left subarray, then you push it back into the push the rest into the right subarray, and then you call merge sort on both the arrays, and that's how we're able to get that branching, as we saw right there. And then at the last stage, when the return condition goes back to this place, it will then call the merge function. As you've seen, we've after we've split so much, we've finally been able to merge. And how do you merge? As I've shown you in the previous example, we check if both the arrays are not empty. So this is actually Python syntax, I think so again. But there are ways to check if your array is empty in other languages as well. This is a bit more Pythonic in nature. Even the reassigning the remaining array is Pythonic. I'm just popping up the other elements, then reassigning the left subarray to the modified left subarray to the new subarray left subarray. So you can see how easy it looks. It looks very difficult, but it's actually very easy. So as I mentioned in the demonstration, you keep checking as long as it's actually not extending out the array bounds by the way. This is right, and then you just add. And just in case I saw on the steps, you violate one of these conditions, if it's is empty actually comes out true, and it'll break out. In this case, you will just add whatever remainder elements are to the array. Do remember that, do understand that only one of these loops will get executed because the other one will be empty. So only one of these will be empty. So, and finally, it will return the array. So thank you guys for coming. Do you have any doubts regarding this session? And I'll be there to take it.
Okay, so the chat box is open. Please, everyone, write your questions.
So I know I was a bit more theoretical today, but tomorrow we'll do one interview question on divide and conquer, and then we'll actually move on to greedy algorithms, and also show you one popular algorithm based on the knapsack problem, which has a greedy approach, and we'll just try one more interview question on that as well. In that phase, we'll actually write some code, okay? And I usually prefer Python. Do understand, guys, that the language doesn't matter whether as long as you can understand the pseudocode. If you can write any algorithm in terms of pseudocode, you can write in any terms of any language. You can just refer to the documentation and see how to implement a loop, how to implement an array, and you can most definitely write the problem. So don't worry about how you should implement it. I know that many interview questions are mostly in Python, Java, C++, or JavaScript, or JavaScript. But don't worry about the language. I do recommend that you learn a bit of every language, but do stick to one that's comfortable for you. Any questions, Jessica?
Yes. Okay, so Anudita is asking, can you explain how did we calculate the time complexity of both best and worst case scenario of merge sort?
Merge sort.
Yes.
Okay, so 1 second. I'm going to share my screen again. One minute, guys. I think there's a bit of technical difficulty. I'm very sorry about that. Give me one moment, and I shall
Yes,
show you.
yes.
Thank you so
Okay.
much. Thank you very much. Okay, got it. So I think the op app is working finally. Thank you so much for waiting, and I'll share my screen again, and I'll calculate once. Thank you so much for waiting. So where's my stylus? Okay, I'm back on the screen right now. So for merge sort.
Yes, for merge sort.
So when you're recursively calling and dividing it into two subarrays, recursively calling and dividing, that is over log of n. It's technically O log n 2, but it's a constant, so we just leave it as that. So how do we get the n part? The n part comes when we combine. So when we combine, as you can see in this step, we have this iterative step over here in this merge function. I'll just put it in full actually, so that you can see as well. Oh, I'm sorry, guys. Where is it? Come on. No, this is for tomorrow. Sorry about that. Oops, I'm spoiling something. Okay. So over here, can you see the merge function over here? So we're iteratively merging n elements technically. So that's why you have the O of n, and you have the log of n because you are recursively calling it into two subarrays, and that's why when you do when you write the reconciliation and when you do that analysis, you get it as n log of n. So just like how I did that, how I derived binary search algorithm right into this. So this is how I got x is equal to n log n. And since I'm doing it for n elements, you'll have to do it n times. So that's why it's like that. So I do recommend that everybody does a bit of research into how into reconciliations. So that's a very important topic, guys. So if you have the time, do look into that. I think if you're in third year, you have design and analysis of algorithms, and that you or data structures and algorithms in second year, I think so, in which you learn it. It's very good to keep those notes for your interviews, because then you can actually uh, learn to implement a bit faster, and it actually gives a bit of knowledge, I would say. Does it answer your question?
Okay, so yes. So the next question is, ma'am, how to practice competitive coding, and at some points in competitive coding, I get completely stuck.
So I'm technically not a computer programmer. Okay, I'm doing lead code. I'll be honest with you guys. The reason why you do lead code is the one thing you learn. You do it is of course for interview prep, because they do ask you interview questions based on lead code. But of course, I have been in a couple of computer programming competitions, and I haven't ranked a lot. But just saying that. So if you I'll write some tips to you guys. One thing: learn fundamentals. So by fundamentals, I mean legit loops, assignments, all that stuff. and learn. And for example, if you do C++, I think many of you use vectors, and many of you use that hash map thing, or I think it's just vector only. I think so. I'm not sure. I'm a Python person. Okay, so if you were, let's just say, a Python CCP person, okay, you would know, like, dictionaries. You would know a bit of NumPy if required, like, just the matrices, and stuff like that. So basically, learn the pre-installed data structures very well. Okay, because if you're pre-installed data structures, you don't need to spend time implementing them as a class or whatever, basically. And you can actually, so this is the case. I think in some implementations you do require to do it from scratch, but if you're in a but if you're in a computer programming setting, right, you can just use predefined classes in that case. So learn your fundamentals, like, learn all a particular language. So if you want to CP, I would say just stick to one or two languages and, like, learn those really well. I think the most popular one for CP is C++ because of the speed of the compilation and execution. But for lead code, I think you can just use regular Python or, like, Java, whatever you want, because it's just getting the output. There's no speed requirement, I would say, in that case. Like, you want processing like like thousand, like, numbers or something like that. So that's one first thing. Learn fundamentals. Second is that it's the easiest and the worst step possible. Practice. There is no secret to lead code. There is no secret to computer programming. There is no secret to interview questions. It's all about practice, practice, practice. I know it's an answer that people don't want to hear a lot, but even I sometimes, like, have difficulty in, like, accepting this. It's all about practice. Here's some tips I can actually give you. So, you have, like, these apps like Notion, which is like, online journals, or you can just use any kind of notebook, even Microsoft Word, or Excel, or any kind of application, or any kind of physical thing that you can touch. So one thing is that you can just create a Excel sheet, or any kind of table, basically any kind of tabular data. So you can maybe have, like, multiple sheets, by the way. So suppose this is about sorting. Write the algorithm. See, okay, now on lead code, you have those difficulty, right? Like, you have easy, medium, very hard, blah, 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 blah. And then you have your difficulty. Like, how do you feel about the question? If you're able to solve it with, like, 5 or 10 minutes, maybe it's easy for you. And then you put a date. When did you last practice this? So here's the thing about acing any kind of interview. You have to do constant practice. You have to come back to the even if you have binary search. For example, I also know binary search, for doing it lots of times. But if you ask me, for example, what is the big O of let's just say binary search, and I'll be like, I don't know, maybe login. I am not 100% sure about that answer. That's because I haven't revised it. The reason why many people are very good at CP, lead code, or whatever it is, it's because they do consistent practice. You keep a schedule for yourself. So use an Excel sheet to keep track of the problem that you've done. Keep track of the stated difficulty, like, like what code share for what lead code, or what hacker rank is saying. Maybe it's easy, difficult, medium, hard, etc. Then you find your difficulty. Do you find, and be honest with yourself, okay? Even if you find an easy problem hard, mark it as hard. There is no shame about this. Like, lead code is, anybody can learn lead code, anybody can do hacker rank, anybody can do CP, in my opinion. And you just have to see your difficulty with that. Let's say for me, medium is medium. This easy problem is actually medium. It's actually bit hard for me. I'll write down the date in which I last attempted this, and I've last found the answer. And after maybe 5 to 6 days, or maybe even 14 days, I'll come back to it and try it again, see if it's better. And of course, you can have one more column for the concepts. Like, for example, you can put DP, dynamic programming, or you can put, like, divide and conquer. You can see greedy over here, or any kind of, like, what paradigm does actually belong to, and you compare. And suppose you can't solve a problem, okay? In that case, now I see that I am lacking in divide and conquer. I will again revise my divide and conquer concepts, and I will again try it again and see how it goes. And it's an iterative process. You do the problem, get the solution, understand it, come back to it again after 14 days, do the problem, understand it, and again do it again. It's constant checking. I believe this is called, like, active recall or something. I am not sure of the studying terminology, I would say. I think it's called active recall. So yes, I know that some people say do 5 easy, do 3 medium, do 1 hard per day, but honestly, for beginners, this is kind of hard because you get very demotivated seeing these problems. But I don't recommend you doing 10 easy problems and be like, I'm done for the day. So if you find that some of the questions you're doing are too easy, okay, go for medium. If you find the medium is too hard, try a bit of the easy problems. If you find medium to be easy, try a bit of hard. If you find hard to be difficult, try some medium. And it's a constant shuffling basically. And honestly, if you practice a bit, honestly, these questions, I don't think you can grind lead code within a single day or within a single month. It is a long process, but do it every day. Keep it consistent. Keep your practice and schedule consistent. If you're going to do lead code at 12 to 2 with 12 p.m. to 2 p.m. with complete focus, do it every day at this time only. So experimenting with what time is actually very functional for you will limit your deep focus. During this time, no music. I know many of us love to listen to music while working, but you should be in 100% distraction free mode. Do you play music in the interview? I don't think so, guys. So no music, no distractions. Best solution for this is that to resist temptations, just put your phone into the other upper to give it to your mom or dad, or if you're living alone, give it to somebody else, or just keep it outside of your room, put it there and just chuck it and just start working on it. If you have any discussions, if you have any distractions again, I think some browsers have focus mode. I am not sure. I just started using Edge right recently. It's actually kind of really cool. So yeah. So as I mentioned, be focused, be consistent. Consistency is the key. It's not about you doing 100 problems in a single day and being like, I'm done for the week. No, it's every single day. A few problems here, a few problems there. If it's too easy, go to hard. If it's too hard, go to easy. Keep a keep tracking basically. Keep a diary or journal or an Excel sheet of whatever problems you solved. So that's my recommended advice. Sorry if I took a bit too much time. Any more questions, guys?
Okay, so Sneha is asking, to someone who has started learning Python, like covered the basic syntax stuff, but isn't able to do the coding questions that well, what would you suggest?
That's what I think. You should spend more time on the fundamentals, guys. That's the thing. So, just asking, what grade are you, or what kind of year are you in? If you can just tell me, I can give advice based on that. But yes, as a general advice, learn your fundamentals properly. See how to do a couple of easy. Forget CP and forget lead code. Learn how to make an average calculator. Insert five elements, find the average. Do a couple of basic projects so you can see how the syntax plays together. Create a calculator, create this, create that. Start doing, yeah. Along with learning fundamentals, guys. I know. Programming languages are not just used for just grinding lead code. It's also used for other things. Okay, for Python, I use it for ML and DL, deep learning and machine learning. So I do stuff with that. So don't make it stale for you guys. Explore a bit of your own language. See how it's being used in day-to-day life. Just don't use the language just for sake of grinding it. Okay. So if you're using Java, you can try exploring. I'm not much familiar with I've used Java for web applications, of course, but apart from that, I'm not sure. I'm not very good at that, but you get the idea. So if you find these things to be difficult, go back to the basics. Learn the syntax. Learn what data structures there. And for example, in Python, you have so many helper functions. Like for example, you have is empty, is capital, is alphanumeric, or whatever it is. Learn all of those. That will actually help you in a very far in the long run, basically. So make sure your fundamentals are the most strongest thing in your skill book. Unless you learn the fundamentals properly, it's going to be difficult in the long run. Don't skip steps. I know that many people learn lead code in 1 month or 7 days, or it doesn't happen. Even MLDL, it takes at least 3 to 4 years, I would say, to get a good grasp of everything. So if you want to learn, start today and keep it going. Basically, any other questions,
Okay,
guys? Good,
okay,
good.
Vijay, sorry to interrupt. So
Good,
Sneha
good.
just completed her first year.
So don't worry, Sneha. So since you finish your first year, I think you've got an exposure to computer languages. For example, I only did like I think first is foundation year for for many Indians, Indian college students, right? Even I also did only C language. I only did C in like my first year. I didn't do anything else. So yeah, even C is a good place to start. Like I think C teaches you very important things like memory referencing, like with and again if you plan to use C++, I think C is a good place to start because you have the memory referencing, of course, operators. So that's a very good place to start, I would say. So if you're just starting at programming, do learn C because it teaches you like not to mess up like easy stuff like referencing and memory management and allocation of, and even teaches you how many like when you do malloc and all, right, it teaches you like the how much memory each item will take, etc., right. It's a very good language to start off with. Do C, learn the basics, learn everything, and start implementing the basic stuff like how to do binary search, how to do bubble sort, just like learn like how to like and think in pseudocode. Guys, don't think in guys please do not think in like Python or C++ or anything. What is an algorithm? It's just a step, it's just a way of writing steps. It's suppose I make a function like bake cake. Okay, let's just say, okay, I'm bad at baking, guys. Don't even ask me about baking a cake. So yes, what will I do? If you have cake starting with zero, let's just say let's give numeric values. Okay, I add I add eggs plus milk plus flour, sugar. I'm just writing something, and then what do I mix the entire cake, and then I bake the cake, and then I eat the cake. The point I'm trying to make with this example is that algorithms are nothing but a set of steps. All you have to do now is think of what steps to do. Now let's go back to my previous example over here. Let's take the easiest one now, just linear search. Okay, in linear search, what am I trying to do? I am trying to find whether a certain element exists. How will I know if it exists? If I can match it, means I can put equal to sign. If I can match it to an existing element in an array. And how do you find an element in an array? By calling its by calling like by putting like this syntax in particular. Let's just say this syntax. So I know how to search and equate for that value, and I know I want to return back that value. Now, how do I go through the array? I start from this first index and I go till the last end of the array. And how will I accomplish this iterative process? By using a loop. Think of it like that. If you're worried, so this think of it as steps. Okay, let's go back to binary search now. Okay, now where's my binary search? Okay, fine. So I give you that. So think of it logically. If I give you an array of all these sort of, if I give you, let's just say I have 8 pots. Okay, I'll think of it like this. I'll just go back to my drawing over here. So let's just think of it in terms of let's just say of binary search. Okay, let's just say this has 2 marbles, 4 marbles, 6 marbles. Okay, fine. I know your human brain will automatically say if you want 6 marbles, you'll pick this. Okay, but suppose you're a computer. Remember, computers are dumb. All they can do is listen to your human instructions. Okay, so so I know that this is arranged in ascending order. So if it's arranged in ascending order, and I want to find a container which has, let's say, six marbles, it will definitely be on the bigger side, on the side of this. So let's say table. This is a table that has more marbles. So I know that this is 6, and let's say this is 7. Okay, I'm just, and there's like one more container having 6 marbles. Okay, I know normally that those 6 marbles will lie between 4 and 7, because 4 is in between 7. 4 is in between 4 and 7. So I will look over here instead. Why should I bother about this side? Why should I bother about this side? Because I know that 6 marbles is more than 4 and 6 marbles is less than 7. Why will I bother about this side? No, I won't look at this side. What's the point of why should I waste time? Okay, now I'm over here now. Okay, now I know that 4 and 7 is in bit is in and 6 is in between these two values. Now I try computing the middle box basically, and I end up with 6. So yeah, it fulfills the condition. It's over 4 marbles. It's below 7 marbles, and it's in the middle. That's how binary search was thought of. So this readjusting of values left and right is just you thinking which side has which has the higher probability of having the marbles. Simple. So think of it in terms of steps. Don't think of it as something that you by heart and you just keep in your mind, just like always use. And if you want, tomorrow I'll even discuss insertion sort, which is a very interesting sort because we've actually used insertion sort in a day-to-day lives. Let's just say you play Uno, or let's just say you just play like regular old playing cards. I think many of us have played Go Fish and all, right? How do we usually arrange our cards? We usually arrange in the order of in an order such that we have the lowest value card at the end and the best value card at the on the right hand side. It's just human nature to do it that way. So insertion sort will do it. Will make, let's say you have like a bunch of cards over here. So how do you rearrange cards? You move the low value cards to the left hand side, and you put the high value cards to the right hand side. So if you want, I'll just do insertion sort as well and show you how the intuitive thinking works. So I do it for sure. I think I'll do it for sure. Before we go into like greedy or any kind of interview questions, I'll do this actually tomorrow. So I'll do it tomorrow. So sorry, any other questions, guys?
Yes, ma'am, which is the best platform to practice these concepts?
Uh,
Like,
so are you talking about programming concepts or talking about lead code concepts?
okay, so Prince Rathod, please mention like which concepts are you
Okay,
talking about?
I'll just say for both. Honestly, if it is the first one, programming concepts, any book, even the documentation is enough, I would say. Why spend money on books? You can just read the free documentation online. And there are so many good resources online. You see New Boston, the New Boston, okay, I think he's retired from making new content, but his old content is still up, okay? He's great at C++, I think even Java, he has made tutorials on what do you call this, on CPP, Java, Python, like just learning like how do you do program in general, all the fundamentals, I would say. uh and there are so many resources online. So you have the New Boston, you have and what else is there? Honestly, I think I have a couple. You know what? Honestly, I think you guys have a WhatsApp group, right, Yashika?
Yes, we have.
I'll mail a couple resources. Okay, so I'll just mail the most common resources for CPP, Java, and Python.
Okay.
For and I'll put in the group. Okay, the WhatsApp group. Okay, I'll send to
Yes,
Yashika, and
yes.
Yashika will forward it to you guys. Okay, so
Okay.
there are many good resources to learn. Um, and if you're doing C sharp, I think the Microsoft documentation is the best. I would say honestly, Microsoft documentation. But any language you learn, if you know the concepts really well, you can easily switch between this language, that language, switch this language with that language. I mostly program Python, but I can easy switch to Java as long as you give me the basic syntax. It's because most programming languages, most high level languages operate the same way, and they're quite similar. Print, okay, what does system.out.println do versus print? Both are giving you print, right? So it's just giving you output. This, this, this are all these operators are common in multiple languages. So it does not matter which language you pick. What matters is how you think about the algorithm, how you implement the algorithm, and how do you think about how do you implement certain solutions. So yes, interview questions have a use. I would say I won't say that lead code is actually completely useless. It is useful, of course. It helps filter candidates because it doesn't filter candidates based on your memory, can you stuff 1,000 lead code within your brain? No, it's teaching you, even if you forget that solution, can you think intuitively to get that to reach the solution. And this intuitive thinking is very important for software development. And that's why software developers are paid quite a bit, I would say. At least in the, I'm not sure about India, but at least in the West, they're highly paid. Like at least 10,000 to like $2,000, I would say, per annum. So yeah, that's what. So if you know a couple of divide and conquer and you give me a different divide and conquer problem, I might be able to solve it because I do have knowledge of divide and conquer. It's all about having that recursion like in a block. You have the combination block and you have the problem solving part, the conquering part basically. So if you can know how to solve these problems, like intuitively you can ace any lead code question. Even if it's hard, you can get maybe you might get a very less optimized output. Maybe let's just say the best solution for that problem is log n. Okay, but suppose you get an n log n answer, your answer will still be accepted for the interview because it's still a good outcome. It's way better than of n square. Okay, so that's why it'll be accepted. So yeah, it shows that you are able to think in an optimal way and you can actually help optimize solutions for the company and you'll be hired. So that's my thinking of it. Okay, I'm not an expert. Okay, I haven't given an interview. All I've done is quite a lot of leadful questions and hacker rank. I haven't done much on CodeChef. I should check out CodeChef. I think it's good. It's also good. So yeah, I'll do that. And of course, the best way to practice is involve in the community. Ask people for help. There are many people that okay, as long as the question isn't Googleable, I would say, is if you can get the answer online. Some people might get annoyed if you ask them the question again because they'll be like, why do you go Google it? But if you have a question like, I understand maybe I understand the recursion and the problem solving part, but how do you best combine the output? Maybe then they'll give you some. Maybe then people in the community will give you good answers. I would say in that case. Any other question, guys? And guys, please don't call me ma'am. I'm like your same age, guys. Oh boy.
Okay, so any more question? Please write on the chat box. Okay, so Nandini is asking, can you explain merge sort?
Okay, sure. I'll do it one more time. Not a big deal with me. Let's make a new array, okay, guys? One second, guys. So I'll teach you the working of it. Then you can go back to the other again. Okay. So let's take some random elements. Okay. 7, 2, 4, 9, minus 5. Give me one more element, guys. Let's just do like one more. I think so. One second, guys. I'm sorry. Let's put 10 over here. 3, 4, 5, 6, 3, and let's just take 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 8. We have 8 elements now. Just like in the previous example, I'll just keep it with you. Okay. Wait, why can't I draw? Okay. So now our first step in our merge sort algorithm was that we find the middle element. So since this is an even array, this is technically the middle element, I would say. So now we'll divide it we'll divide it into 2 subarrays. Okay. So till this element ending, we will add it into the right subarray. It's just starting of that. Yeah, it's the starting of that recursion. Okay. So now we have 1, 2, 3, 4, 9, 5, 3, 8. Okay. And now let's just move a bit down because I don't have any space. I'm so sorry. I'm like writing a bit big. What is this? No, I don't want to. I don't have to do anything. And again, till we hit only single element arrays, we'll keep dividing. Okay, again, this is our middlemost element technically, so we'll just divide it again. 7, 2, 4, and now we have 3 and 8. Okay. Again, one more time we divide because we have to hit that one this thing. So you have single element subarrays. Okay, now let's start our so all we've done now is that we have done the divide phase. Okay, so till here we have done the division. Okay, the divide and conquer in the entire divide and conquer algorithm. This is our divide phase. Okay, now we'll do the conquer phase. That is basically solving the problem, because we have such, now we have divided into small chunks. We can manage it much more better than a huge array. Okay, now let's start thinking. Okay, now this is my left sub array. This is my right sub array. Okay, now I will keep taking the first element of this sub array, and I will check which first element of which sub array is the smallest, and I add it to the final result array. Okay, this is my result array. So now a 10 and 7, which is smaller? 7. And now since I'm popping this element out of this array, this is the loop for adding has been broken. This loop, 1 second, if I can just get it over here. This loop that both the subarrays should be empty. One is violating, and this is an AND condition. So for this condition to hold, these two have to both be true. This is giving us false. We break out of this loop. Now one of our arrays is still not empty. So we will add those remainder elements into the final result array. Now this is my remainder, remaining basically. When I say remainder, okay, not the division remainder. Okay, so this is our first combination, our first conquer. Okay, we've conquered this problem. We've conquered this. We've won this battle of, like, sorting these two subarrays. Now, in this case, we'll pop this. We'll hit that condition 2 and 4. Now minus 5 is smaller than 9, so 9 comes first. Now 3 is smaller. So our first set of conquering is done. Let's do the next phase. Oh no, I can't see the elements themselves. Wow. Okay, now we have slightly bigger arrays. Okay, now let's see. What's our first over here? Our first is 7 and our first is 2. Which is smaller, guys? 2, right? So we'll put 2 first. This has been popped out. We've removed this element from the subarray. Now this is our first element. Which is smaller, 4 or 7, guys? This, right? Popped out. Now this is broken the condition of that loop. We'll go to this now. We'll add this entire subarray, remainder of them, in the same order, by the way. We don't change the order, okay? Okay, let's go over here. Which is smaller, guys? This is first. Minus 5. Popped out. Now this is first. Which is smaller, guys? This. Which is smaller now? When this is first. 8. Condition is broken. Now we have 9. Remainder. We'll add this. Okay. Now our second conquering is done. We've finished off this conquering. Okay, we've won this battle again. One more time we have to do this. Okay, then we'll win the entire war, basically. That's what we call it. 2 versus minus 5, which is smaller, guys. Minus 5 popped out. Our next first is 3. 3 versus 2. 2 wins. Now this is the first array. 3 versus 4. 4 versus 3. 3 wins. This is the one. 4 versus 8. 4 wins. 7 versus 8. 7 wins. 8 versus 10. Which one wins? 8. 9 versus 10. 9 wins. And then our remainder element we'll just get added to the last, which is 10. And now we have our sorted merged array. And this is our final output. So by just winning small battles, we've won the entire war by conquering it. Simple. So it's just breaking down. Same thing. If I tell you to study an entire chapter, are you going to do the entire thing at a stretch? Probably not. You're going to do the first section, take a break, go for some tea, come back to the second section, go and play on your phone for some time, come back, finish the third section. Okay, fine, let's do it now. That's what it's solving the bigger problem by solving smaller sub problems. So just to give you the entire view, basically, I'm just gonna like show you guys. Okay, I think mine is like way too big. I'll just make it. And so this is how we've first divided and then we finally conquered. And this is our merge sort. Yashika, do you have any more questions? Does it answer? Is it clear now?
Yes. Okay. Okay. So I think no more questions are there. Okay. So one last question is there: how merge sort will work in case of odd array index?
Sorry, in case of
In case of odd array index.
odd array index, as in I don't get you. Like it starts from one,
Rohan,
or
can you mention the question once more properly?
are you talking about it being having like let's just say seven elements instead of eight?
Yes, I think he's asking about odd numbers.
Okay. I'll make it. I'll just show you one small division based on that, and you can just understand it from there itself. Okay.
Okay,
I'll
okay.
just show you. Okay. So once again, I'm going to share my screen again. I'm so sorry about stopping it. Okay. So here's okay. So fine. I'm going to erase the entire thing. Okay. So I know I've used eight numbers because it's like easy to show that it's equal. Okay. Now let's do let's just take three elements. Okay, of merge sort. 3, 2, 1. Okay. Now it's like the worst case scenario actually. So what's the middle element? This one, right? So it starts splitting from here. Okay, this is one, guys. One. Okay. So let's divide. 2. Now this has already hit that escape condition. Okay, guys. So within the first step only, you hit the escape condition. Okay. I don't know, like over here. This is hitting the escape condition. This will again divide amongst itself. So it doesn't matter if your array is odd or array is like has odd or even numbers. So this will again merge. Now 2, 3 will happen over here, and now this will come down. Where's the pan button? Okay. Okay, fine. Now let's do it again. Okay. So first element of this is 2. First element is 1. Which one comes first? 1. This gets popped out. This is the first one. 1 versus this remains actually. I'm so sorry. This one gets popped out. Now all you have to do now is since this is breaking the condition because it was a single element and we finish it off. Now the is empty condition is saying it's false. So now we will just add the remaining elements of the other subarray without changing the order. Now 2 will get appended, 3 will get appended, and here we go. We have the same merged inserted array. So does it answer your question, guys? So okay, sorry for this scratch. I'll just zoom out and show you so that you can see how it goes. Like this, guys.
Okay. So I think there are no more questions left in the chat box. So we are wrapping the session. So thank you, Vijaya, so much for this long and clear explanation.
I
Okay,
hope it
you
wasn't
have
too long.
explained.
Okay, I think I talked too long.
I think you explained very well and in a very organized manner with showing so many examples. So thank you everyone, thank you Vijaya, and thank you everyone. So we'll share you the resources which Vijaya will share to me, and I'll share with you the resources on WhatsApp. Okay. So thank you Vijaya and thank you everyone.
Thank you, guys.
Okay.